Slides just to make sure.
Yeah.
Oh,
Nope.
Yeah,
Who was that?
yeah. You've turned
Okay.
on. You've turned us
Okay.
out of practice mode.
Okay. Sorry, I just click on this. There was a thing coming on my
Max, you
screen.
might want to.
So, hello everyone, and welcome to this week's EMinar. So this week we have Romain Corseri on 3D magnetotelluric image of a hyper-extended and serpentinized rift system in the southwest Barents Sea margin. Before Romain starts with his presentation, I just want to show you a bit of the upcoming talks that we have lined up. So if this wants to go, yeah, next week we have Janelle Simpson talking a little bit later than usually at 9:00 p.m. Universal Time, talking on using MT to understand the Mount Isa province. In 2 weeks' time, Ian Ferguson will talk on nuts and bolts of magnetotelluric instrumentation and fieldwork. So that's going to be an interesting one for anybody who's involved in acquiring MT data. The week after that, Raphael Rochlitz on CusTM from open source 3DM modeling towards inversion. So another inversion code that could become interesting in the future. On the 23rd, we have Simon Jowett on mining for new zero. I think that's supposed to read net zero. In any case, something going slightly beyond just EM, but sort of putting it all into a bigger context. And then, well, the final one in this announcement, you can find the other ones online. On the 13th of March, Seogi Kang on advancing Earth imaging techniques for improved understanding of groundwater systems. I assume by now everybody is familiar with both the website and how to participate in a Zoom webinar. Here, just the address where you can find all the EMinars. You can also find video links to previous presentations and the slides if the speakers have made them available. And we have the typical Zoom settings here. The webinars are slightly different. The main thing to consider is that if you have a question, please write it in the Q&A and not in the chat. And with that, I'd like to hand over to Romain. I don't have a CV or something from you right here, so maybe you can introduce yourself with a few words before your presentation.
Yes, so thank you very much for it. So my name is Romain Corseri. I'm a geophysicist by background. I've been working with marine electromagnetics in the industry before, so mainly for hydrocarbon exploration in marine offshore projects. So now I've been actually been a PhD candidate for the last 2 years, and I've put together the project that you're gonna be that I'm gonna present today, which is a joint industry academic project dealing with the MT in the Barents Sea. So I will share my screen. All right, are you? Can you see my screen and hear me? Okay.
Yeah, all good.
Okay, very good. Thank you very much. So, so today I'm going to talk to you about an MT image of a hyper-extended and serpentinized rift system in the southwest Barents Sea margin. So, as I was saying, this is a joint venture, industry PhD project that is financed by the Research Council of Norway. So my academic supervisor are part of the University of Oslo, where I am affiliated to the department. VBPR is my industry employer, and EMGS has been kindly providing the time series, the electromagnetic side time series that I've used for this project. So of course, I thank them a lot for supporting this. So this is the outline of my presentation. So divided in two. So the first part will be dealing with introducing the project, the motivations, the database, which is consisting of marine MT data and other type of geophysical data, data processing and analysis. So This is actually, first part is more of a data domain analysis presentation, and the second part will be dealing with exploring the model domain, so the electrical resistivity of the Earth in the Barents Sea, and what it means in terms of geological processes. So the motivations. So what you can see here on the right is a typical marine EM survey setup, laying receivers on the seabed, recording the horizontal electromagnetic field. So in the case of magnetotellurics, we are dealing with the natural variation of the horizontal electromagnetic field. Assuming that the source is very far away, then we are dealing with a plane wave that's incoming the Earth. So this is a large-scale geophysical methods that you, of course, all know about. And we can probe the electrical resistivity of the Earth down to the mantle. So typical offshore MT periods are between 1 and 5,000 seconds. So here is a map of the Earth, and you can see on the dots are marine MT survey for active margin studies. So you see there's actually a wealth of research that has been done on ocean ridges, subduction zones, hotspots, mainly EMinar and Scripps Australia as an institute, amongst others, have been acquiring this data. So there's actually a wealth on active margins. So here is some important works. So Kerry Key and co-workers on the East Pacific Rise. More recently on the North Atlantic, Johansen have been imaging this melt channel beneath the Mons Ridge. Some other work here in subduction zone in the Pacific. So in this type of setting, actually the heat source and the melts are actually targets of the MT studies as a conductive zones. However, in passive margins, there's actually very scarce studies that have been acquired in marine settings to study the tectonic development of these rifted margins, probably due to high operational cost and the complexity of thermal and structural processes at stake. So you see here some important work. So offshore Western Australia, Einstein have been actually detecting graphite layer in a shear zone on the mid-crustal part. And you see on the right, Yegen et al. Imaging actually magmatic processes in the rifted margin offshore Namibia. So when you see these studies and you look at the distribution of passive margin in the world, you can see that actually there's very little is known about the electrical resistivity structure of rifted margins and what they mean for rifting and continental breakup. So why would we study this passive margin? What would they bring to the knowledge? So first of all, it's an important point in understanding past and current climate changes. For example, by reconstructing the plate configuration in the past breakup of Pangaea, for example. It has also an importance for carbon cycles with the greenhouse gases that are released during the opening of ocean domains. It's also an important point of the interaction between the fluid Earth and the solid Earth. So how, for example, water would be transferred to the deeper mantles, and finally, it holds significant hydrocarbon reserves. So this is why we study passive margins. So next, I will show you the marine MT database that I'm using for my research. So the story takes place actually in the Barents Sea. So the Barents Sea is an epicontinental sea located at the crossroad between the North Atlantic regions here that you see Greenland and Norway, and the Arctic zones. So you see Svalbard, Novaya Zemlya. So the Barents Sea lies at this crossroad, but we will mainly look at the geology in a North Atlantic tectonic framework. So this is a bathymetry of the study area in the Southwest Barents Sea. You see it's a rather smooth bathymetry. mainly between 300 and 500 meters. So the fact that it's smooth is quite good, especially for inversion. And what you can see here is actually receivers that have been laid on the seabed by the industry over the last decades. So I haven't counted them, but there's been 1,000 of them. So each color represents a survey. So you can see that this is probably one of the largest marine MT database that has been gathered on a marine setting. So for my research, I had access to this database, and I've extracted actually 6 transects and 337 receivers. And these transects were designed to actually cover some structural elements here of the Barents Sea. So for example, you have here the Stappen high, which is actually a basement high, so where the continental crust is very thick. And you have here in green some rift system or basins that have been where actually the crust has been highly thinned. And on the eastern part, you have more like a continental platform and a more stable sedimentary platform. So this is for the geological setup of the database. So now I'm going to go through a bit of data processing and analysis. So I've been using the robust multi-station data processing schemes first designed by Gary Egbert. So in this processing scheme, we group receiver together and we try and find some coherent signal to extract the magnetotelluric data. However, for this data in the Barents Sea that were required primarily for control source electromagnetic, we have an active signal coming from the source. And it has to be masked in order to be able to extract the proper MT data. So what you see here is a spectrogram. So it's after Fourier transforms of the electromagnetic time series, you extract amplitude and frequencies of the signal. So you see here very well like the background signal where the signal is strong is red and blue is weaker. So here you increase the frequency. So what you can see actually here in this vertical sign is actually the signal of the active source that is actually emitting a signal that has actually a distinct source harmonics. So part of the work I've been first to go through all these time series and remove these active source signal that we're not going to use. So then going through the multi-station processing. So what we want is the magnetotelluric impedance tensor. So the impedance tensor embodies the response of the subsurface in response to a planar electromagnetic wave. So it mainly links the horizontal component of the electromagnetic field. So you can see one example here to the right of apparent resistivity response and phase response. So to show how does the data looks for you, I picked a few examples that are, I think, quite important. You can see the diversity of the MT response. So for example, here on the Bjørnøya basin, which is a very deep sedimentary basin, you can see that the apparent resistivity sense actually, you can see a descending trend. So as you go deeper in the earth, you can sense a more conductive earth. Whereas where you go on the Lopa highs or where the crust is quite thick and shallow, you can see the apparent resistivity is actually climbing up. Here you have a bit more complex phase response, probably due to the presence of salt structures. So indeed, that's here a pseudo section of the data. The two component of the two non-diagonal components of the impedance tensor, apparent resistivity on top and phase on the bottom. So I'm showing you here because I think it really shows that there's actually a lot of geological information in this data that have been extracted from CSEM industry surveys. So as I was saying, in the Bjørnøya basin, deep sedimentary basin, you see a descending curve, whereas when you go more to the the part where the crust is very thick, you can see a very different type of response. So indeed, there is a lot of information on the Earth in this empty data. On top of this, you can see here is an apparent resistivity map, extracting actually at each receiver the apparent resistivity of the YX component at about 500 seconds, which would correspond approximately to a mid-crustal depth. So what's interesting here is to see that you have actually a very, very abrupt change when you go from the sedimentary platform and where the crust is thick to the rifted and deep basin domain when you go to the west, which is actually very conductive. So you have almost a 2 to 3 orders of magnitude of resistivity change from east to west. So another important aspect of marine MT is actually the electromagnetic strike. So this electromagnetic strike is actually represent the main direction of the regional resistivity structure of the subsurface. And often the geological strike corresponds to the electromagnetic strike. So in a 2D world, when we rotate the impedance tensor along this EM strike, the impedance tensor takes a more simple form, where actually the diagonal elements are null. So if we want to do 2D modeling, we have to look for this type of configuration. So often we show this EM strike analysis on the polar diagrams. You can see here. So going through all periods and look for this angle that minimizes the diagonal element of the impedance tensor. So you can see here on this particular example, you can see that the strike is quite actually clear, 170 degrees east. And often in some places, you have a period-dependent strike angle. So it may correspond to a subsurface that has two, for example, superimposed tectonic fabrics. So you can see sometimes that this electromagnetic strike can be period-dependent. And in this case, it can be quite important to use 3D modeling instead of 2D. So this is the outcome of the dimensionality analysis in our database in the Barents Sea. So what you can see here is actually a split that's quite obvious, where to the east you have a more complex orientation of the preferential currents, actually mainly divided in 2 directions, so a period-dependent strike. And if you move to the west, where you start to see the influence of the North Atlantic rift systems, you can see that the strikes has a north-south direction dominance. So this is important when you actually plan your modeling strategy, whether 2D or 3D. So of course there is an ambiguity when you actually determine the strike angle. So there's always this 90 degrees that ambiguity that you have to lift, and we lift it because we actually know on this part, on the western part, we know that the currents would actually flow along the continental slope, or along the breakup axis of the margin, which is the most dominant geological feature. So we could unambiguously determine the EM strike here, thanks to the geological knowledge. So now we move on to part 2, and we're going to explore more on the modeling part and the geological implication of it. So we actually use a subset of the database that I've introduced to in the first part, and we actually going to focus on this deep basin called the Bjørnøya Basin, and you will see why it's an important feature of in the North Atlantic. So we actually, you can see here empty receiver laid on the seabed, and we divide it in 3 domains that we're going to use in a different inversion domains, actually, just to optimize the computational costs. Yeah. So why is this basin so important? It's actually part of a crater's hyperextended basin chain that extend from here. You can see the West Orphan Basin offshore Canada, through the Rockwool Trough west of Ireland, the Murray Basin on the Norwegian Sea, and finishing up to the Bjørnøya Basin to the north. So what we are looking at and what we're going to study here could be extended to this early Cretaceous basin chains that almost reached the breakup phase, but failed before. So indeed, you can see here actually a crustal section in the Bjørnøya Basin by Jarnigon and co-workers. And what you can see here is that this model was derived from gravity and seismic data. And actually, there remains an ambiguity with the interpretation of a deep and lower crustal structure there. Indeed, it is often the case that seismic velocities and density values doesn't allow to conclude on the type of lithology that's beneath the crust or in the crust. So they often denoted as lower crustal bodies or high velocity bodies. And these actually could be well altered mantle or serpentinized mantle, or lower crustal bodies like magmatic underplated. And this is quite a notorious challenge when dealing with rift systems. It is often non-conclusive when using magnetic density models. And so we want to see if actually electrical resistivity model can help to disambiguate this type of interpretation. So, so the method, so the tool I'm using in my research is ModEM, and more specifically the Mod 3D-MT modules. So, of course, I thank the authors for providing an academic license for it. So you can see here the main reference. So the principle of this inversion scheme is actually based on the Occam razor, so where plurality is not to be posited without necessity. So it means that in my research, I will be seeking the smoothest or the simplest resistivity model that will fit the observations. So this is the decision that I took, that not to include, for example, constraints from known geological boundaries, and let the data speaks. And other people have done joint inversion, but this is here using empty only inversion. So the objective of the inversion scheme is to minimize an objective function that you can see spelled out here, that has a data misfit terms, but also a regularization term. So first, I'm going to show you some synthetic testing. So the aim of this synthetic test is actually to try and anticipate what type of imaging we can expect from magnetotellurics inversion there. So for example, here you can see on top is a typical or archetypal rifted margins with a different tectonic domain. You have here the proximal domain where the crust is actually undeformed, and moving on to in the more distal part of the basin, the crust is hyperextended and usually defined as thinner than 10 kilometers. So what can magnetotelluric inversion can do here? How can it reconstruct the crystalline crust, for example, or prop the resistivity of the altered mantle or the upper mantle? So that's all this synthetic work is made to help the interpretation of the resistivity structure in the real data inversion. So what you can see here is to the left is what we call the true resistivity model. So we generate synthetic empty data along these four models, and we invert them back. And of course, we try to mimic as close as possible the real data conditions. So we actually copy and paste the survey setups, the noise, the period contents, the bathymetry, and we try and anticipate the behavior in the inversion. So what's interesting here as you can see on all three models, is that when the crust is hyperextended, the inversion doesn't manage to reconstruct the crystalline crust. So it is too thin to be reconstructed. So the sensitivity is probably too low. So that's an important point. So when dealing with empty and passive margin, we can expect that we will not recover the resistive crystalline crust when it is hyperextended. On the other hand, it gives also a window to probe the upper mantle resistivity values here. So you can see also here I've introduced a basin conductor, so a very conductive layer below 1 meter in the basins. And you can see that it is actually affecting the imaging of the upper mantle below by also like dissipating the energy. However, you can see that whether you put an altered mantle or not, you can see that the upper mantle would be imaged also as a sort of a tail of this conductive anomaly. So when it is not present, you can see that this conductive tail is not actually imaged. So this is important to sort of distinguish between what comes from the basin and what would come from the upper mantle in hyperextended zones. So now we move on to the real world and the real data inversion. So what you can see here on top is the electrical resistivity model along this particular transverse going from northeast to the southwest. So it's encompassing the stable platform and going through the very hyperextended basin here. So you can see the most prominent feature of the model. So you can see that conductivity is actually present in the deep basin, whereas where the resistive crystalline crust is present, you can see resistivity values up to 100 meters. So this is the part of it, actually the electrical resistivity model that goes actually in the perpendicular direction. So you can see this model cross at the Björnøya basin, and you can actually recover a similar feature. So the highly resistive crust is recovered properly, but when we move on to the hyperextended basin, and as expected from the synthetic test, the resistive crust vanishes, and what we can see is actually a prominent conductor about 10 to 15 kilometer depths that's actually reaching 0.1 meter. So it's a very, very, very low conductivity zones, and leading to this conductive tail here that we will call C3, and actually encompassing the uppermost mantle, and has values spanning from 1 to 10 meters. So this is the most important result of the inversion that actually has reached quite a low misfit. So you can see on top 1.07. On the Stappen height, it's actually a bit higher, probably because of the proximity of the bathymetric slopes, 1.4. And for this part of the model here on the red inversion domain, you can see we reach 0.9, so quite low misfit values. So this is a model slice. So at 10, 20, and 30 kilometers, you can see that actually the conductivity zone is actually limited by the actually really well located in the Björnøya basin, the rift, the hyperextended rift. What you could see here is actually the normalized RMS misfit values per receiver and per component here. So this is just to show you that actually the inversion has been working quite well at minimizing the misfit and reaching actually quite low values, especially in the basins. So the inversion has been performing well here. Of course, when we have our electrical resistivity model, we have to test it for robustness. So are the anomalies that we are recovering, are they real? Are they artifacts of the inversion? So we actually took every of these prominent feature that we've described earlier and run them through this procedure called hypothesis testing. So you can see one example here for the basin conductor. we actually erased all the resistivity below 1 meter in the anomaly, and we run a forward model and see how the RMS is affected by the removal of this anomaly. So you can see here the distribution of the RMS for the inversion model, and when it is altered, so when the anomaly is removed, you can see that the RMS reach very high value, so above 5. So you actually increase the RMS by 5 to 6 times, which is well beyond the data uncertainty. So you can expect that this conductive feature in the basin is actually a robust feature. So then we move on to geophysical data integration. So that's good. We have our electrical resistivity model, and then we want to confront those models to the other geophysical data that we have in the area. So taking the east-west electrical resistivity model, I'm actually using seismic refraction data that you can see here. This is in the time domain. So we actually use stacking velocities and a constant velocity for the resistive crust in order to depth convert our seismic interpretation. So what you can see here is the result of this seismic interpretation, but depth converted. So what you can see is interesting here is that this really high conductivity zone seems to be constrained to actually the deep sediments of the Björnøya basin. And you can actually see that actually the conductive zone beneath is related to the upper mantle. On the other models, the one that's going north to south and encompassing actually across a large and ample crustal variation, what you can see here is seismic reflection data, actually deep long offset seismics. So you can see here that we can also extract reflectivity from the lower crust that you can see here. So here we have a nice image of what could resemble the crustal variation from seismic reflection data. So what you can see here is, as expected, when the crust thins out and the basin is deep, the crust is hyperextended, and we of course do not recover the resistivity, the resistive crust. Using this seismic interpretation, you can see here that actually the conductive, the very low conductive zone below 1 meter is constrained to post-rift sediments that are mainly of Cretaceous age. So you can see that it's quite unambiguous that this conductive zone is actually constrained to the basin sediments. So that will have to be considered in the interpretation of this resistivity models. To the right, you can see here, this is actually the model from potential fields, so from magnetic and dense and gravity data. So what you can see here is actually the top basement from magnetic data as recovered by Jernigan and co-workers. So to the bottom here, this horizon corresponds to the MOHO according to gravity data. So what's interesting here is that the conductor beneath the basin is actually corresponding to this so-called high velocity and high density zones. So now that we have described all of our geophysical data, we can try and move on with confidence to understanding what's happening in the geology of the area. So we're going to discuss mainly the conductive zones, the very high conductive zone in the hyperextended drifts. These are the most important feature of this work. So usually when we talk about high conductivity in the crust, mantle, or sediments, we usually deal with 3 options. So first of all, you have the presence of melts. So presence of, for example, a melt reservoir beneath a volcanic edifice usually display a very conductive behavior. You can have conductivity related to remnants of intrusive and igneous activity in the earth, So, for example, igneous intrusions, seals, etc. This can lead to mineralization in the contact areas and can have very, very low conductivity. And the third option is actually saline fluids. So in the interstices or in the pore spaces of these sediments or the upper mantle, you can have fluids that actually create conductive anomaly. So in this part of the world, in the Björnøya basin, we actually can safely consider that partial melt and high temperature is not the cause of this conductivity. This is quite actually in terms of heat flow, it's quite let's say normal heat flow. There's no anomalies there. We don't expect the presence of melt in the basin. In addition to that, we have not in the seismic data, there's no signs of igneous activity or seals or related intrusions. So we can also discard this hypothesis where mineralization along intrusion can trigger this high conductivity. So actually, we invoke saline fluids here, and we will see why we think this is the most robust interpretation. So for the interpretation of this anomaly, we use a model that describes the bulk resistivity of a two-phase rock fluid media. This is mainly inspired from work from a model described in Renard et al. 2011. So in this model, we relate actually the bulk resistivity of a volume of the Earth, and we relate it to the conductivity of the fluid in the pore space or interstices, and the matrix, the rock matrix. So we will start with using this model for the interpretation of the upper mantle anomaly T3. That's, you can see, is imaged as a conductive tail of trailing beneath C2. So C3 has a conductivity values ranging 1 to 10 ohms. So how can we explain this high conductivity in upper mantle conditions where you have actually a very low volume fraction? So we can safely say that around 1% is a realistic estimate. So, for example, here you can see this bulk resistivity relate to the volume fraction for a different type of pore fluids. So at upper mantle condition, seawater is known to be approximately around 0.003 ohm meter. So that would be the seawater buried at this depth. So what you can see is, to explain this anomaly, you actually need to have a much more conductive fluids, much more than seawater. So we know that in the crust and in the sediments, seawater is the main saline fluid reservoir. So to account for this anomaly, you need to transform this fluid and make it more saline. And to make a fluid more saline deep in the earth, you actually have to increase its salinity. So that's here the second part of the graph here. That's relate bulk resistivity to fluid salinity. And you can see that in case of T3, if you want to reproduce the strength of the anomaly, you have to increase around 5 times the salinity of the fluids. So how do we increase the salinity of a fluid in the upper mantle? So the serpentinization is actually can be the cause of the increased salinity down in the upper mantle. So a very simplified illustration of serpentinization is illustrated here. So it's when olivine-rich ultramafic rocks of the upper mantle reacts with water and produce serpentine. So in this reaction, pure water is consumed, and the residual fluid is actually increasing in salinity. So that's what's reflected in this graph. You can see here, I'm trying to illustrate the change of salinity of the fluid in the pore space. And as you increase salinity, it actually means that you increase the degree of serpentinization of the crust. For example, here in this formula here extracted from from Reynard model and reference therein. So actually, if you have as an incoming fluid the salinity of seawater, and you increase it 5 times as we need to have it to explain our anomaly in the upper mantle, you have to increase it 5 times. It actually corresponds to 25% degree of serpentinization of the upper mantle beneath the Bernina basin. So indeed, we think that by using electrical resistivity model, we can actually distinguish between lower crust and upper mantle in this type of setting, and actually decisively interpret the lower crust as a serpentinized altered mantle. As I was showing you earlier, the density and gravity derived from gravity data shows that in the upper mantle you have a quite dense value. So is this density value of 3.1 kilogram per cubic centimeter compatible with serpentinized upper mantle? So we verified that with actually empirical relationships that have been derived from actually samples of serpentinized mantle, actually from Pinto et al. So you can see that if you want to have if you have density of 3.1, you actually corresponds to approximately a 25%, between 20 and 30% serpentinization. So the interpretation we made of this conductivity as a 25% serpentinized mantle is actually compatible with the density values from gravity data, and also compatible with the seismic velocities that have been extracted from refraction studies there. So anyway, it sort of fits. It fits very well. So we have all used all this geophysical data in their own domain, and we put them together and check that for their consistency and actually support our model of serpentinization. And actually, we can actually find clues of this serpentinized mantle in fossil hyperextended system. Here, this is a picture from Colta et al. This is an abducted system in the Pyrenees, and geologists have been sampling, and they actually could track the remnants of fluid, residual fluid from serpentinization up in the crust and along the attachment fault that you can see here to the right. So from these fossil systems, we know that actually fluid are circulating in this rift system, and they actually can ascend through faults from the upper mantle and contaminate the sediments in the basins. So that would lead us to the interpretation of the basin conductor. So we have imaged quite strong and prominent conductivity below 1 ohm meter in the deep sediments of the basins. So this is a robust anomaly, and again, it cannot be accounted for if we only consider that seawater is the only saline fluid in the pore spaces. So by showing you this example from the fossil system, we know for a fact that residual fluid from serpentinization that have increased salinity can migrate and contaminate the fluid in the pore space of the rift sediments. So that would lead us to these ideas that I'm defending here, that magnetotelluric is actually it can actually illustrate a model of saline fluid circulation in hyperextended rift systems. So you can see here an illustration in a 3D view of what I've been talking about. So what we defend here is that our electrical resistivity model and gravity and seismic data actually can be reconciled and in this present day rift system, and fitting with also geological sample from fossil systems in the Alps or in the Pyrenees, and point to this saline fluid circulation. So during rifting and hyperextension, seawater is in the pore spaces of the sediment that are being deposited in the subsiding basin, is infiltrating down to the upper mantle that is embrittled, and serpentinization can occur. So this is a documented phenomenon. We know for a fact that serpentinization occurs in a rift system, and seawater migrate through the through faults. What is new here is that what we show here with this magnetotelluric is that this mantle-reacted fluid can actually migrate up and contaminate the post-rift sediments that are depositing in this subsiding system. So this high salinity from serpentinization can actually mix with the seawater in the marine shales, for example, and would explain the resistivity, the conductive anomaly that we see in this in the model that I've just extracted in the SW Barents Sea. So so that's here. That delivered on my promise. So to actually try and explain what's happening in the Earth. So we started with the MT data and the time series, and we have try and achieve this goal of understanding deep saline circulation in a rift apparent rift system. So we believe that this model could be used in a hyperextended rift system worldwide. So especially in the North Atlantic, where this early Cretaceous rift failed basin chain is encompassing the whole North Atlantic. So that would finish actually my conclude my presentation. So I would like to acknowledge my supervisor team, Sverre Planke, Jan Inge Faleide, Kim Sanger, Leif Jakob Gelius for their support, the Research Council of Norway for research fundings, the ModEM and NTPI code author for providing academic license to use their tools. So I would like to thank you as well for your attention. And if you want to follow my research and get in touch, you can use my Twitter or LinkedIn profile, or send me an email, and I will be really happy to answer your questions. Thank you.
Thank you very much, Romain. That was very interesting. And now there is an opportunity to write questions in the chat for those of you who haven't participated in one of these yet. I will read out the questions so that they're in the YouTube video, and then Romain can answer those. While we're waiting for people to type, I have a couple of questions actually. So the first one is, I mean, I understand why you don't use all the data. Yes, I mean, what you showed with those 3D patches, they're made for hydrocarbon exploration, and you have sort of very heterogeneous density. I'm wondering though why you concentrated on profiles with sort of fairly big gaps between them and didn't sort of look for, let's say, a slightly more even distribution in 3D.
Yes, so that's actually a good comment. So it's the idea when I was given access to this really large electromagnetic database was to sort of let's say probe for the scientific potential for this data. So I was trying to design these transects in 2D actually to try and see where the data was interesting and in the shelf scale. So indeed, it would be beneficial if actually when dealing with actually this rift basin to have actually 3D coverage, which actually is available. So in a way that will basically follow up on this work. It's actually, if this is such an interesting zone, then it should be of course dealt with in 3D with actually a 3D coverage. But of course I don't have unlimited access to the industry data, but that was the idea, is that to actually try and probe as wide as possible this EM database. I
see. Yeah, of course, it's always sort of a compromise between sort of practicalities and what you do in the beginning, and then sometimes these decisions sort of follow you through for quite a while.
That's correct.
And then a second sort of question / comment, because you said I want to, I'm not interested in sort of preconceived models. Yes, I want to do sort of a neutral analysis that's, and do this smoothness-based inversion. From my perspective, I think, especially when you show the comparison with the reflection seismics and the magnetics, something like constrained inversion as a sort of hypothesis test for some of those things, I think would be very interesting because, as you showed with your synthetic examples, a lot of this stuff sort of bleeds down. And if you, test if you have certain structures or if certain structures can be present at certain depths, I think that can help you to get more answers from what you're trying to do.
Yes, so I agree with your comments. So that could be really interesting, interesting test to do. But I have to sort of make a comment on this. Is that, for example, the MOHO as a boundary is defined, of course, by seismic velocities, and we actually know that it's not actually translating as a resistive boundary in the electrode. So would that be correct to introduce that in the inversion? I'm not sure. And another point is that, of course, potential field has a high non-uniqueness component to it, because these are derived by forward modeling. So of course, if you introduce these boundaries, you should be really confident that they represent a true geological resistivity boundary as well.
Well, the way I would look at it, and then we'll sort of move on to the next question, is it's also like another form of a hypothesis test. Yes, you say, okay, can I make a model that looks like that, and then sort of maybe use the inversion to tweak that model. But because what you're saying, of course, is absolutely right. You have to be careful not to just put your ideas in and get your ideas back out. Yes, that's very dangerous. Okay, we have a question from Hanan Rivas. Hola, Romain. Thank you and congrats for your presentation. Very complete and interesting. A question: have you ever recognized static shift issues in marine data sets? How do you deal with that?
So, as far as I know, there is really little static shifts in the data. Actually, I haven't seen a receiver that has static shifts, and that may be a characteristic of the marine data. But I wouldn't be able to explain you in detail right now.
Yeah, I mean, I'm not an expert on marine EM, but I think it's the seawater on top, together with the generally conductive sediments, it sort of prevents a lot of that. Then we have Peter Klitzke.
If I could just jump in.
Sure,
Yeah, just to answer that question, I think you won't see any galvanic distortion of the electric field, but you might see galvanic distortion of the magnetic field, and it'll be very subtle.
Yep. Thanks, Alan. So Peter Klitzke, many thanks for your interesting talk, Romain. Do you see resistivity trends within the interpreted serpentinized mantle, e.g. with distance to main faults as fluid pathways?
So I haven't gone in this type of details yet, but the trend would be that, of course, the resistivity would be, the conductivity would be higher in the uppermost mantle and decrease when you go down to the mantle at depth. So this might be really a regularization artifact, or this might be actually an effect of the decreasing degree of serpentinization as you move in deeper in the mantle.
Yeah, thanks. Yeah, I think you're exactly right. The regularization, of course, is a tricky one there, because it can create sort of similar images. Okay, let's see. I don't know, Alan, do you have a question?
I do actually, Max, if that's okay.
Sure.
Romain, first of all, a wonderful talk, absolutely brilliant. I loved it. With the MT method, of course, we have very, very poor resolution of the actual resistivity below conductors. And so I'm just looking at your model. What I see is quite strong vertical smoothness, but weaker horizontal smoothness. I'm just wondering whether, in fact, as a hypothesis test, you could have the resistive crust underneath your C2 conductor. I'm questioning the existence of the top of C3.
Yes, and I think that's a very good comment, and it's actually something I've done myself. So I've introduced this resistive crust in below the basin conductor, and actually you can see a perturbation in the RMS value. So I'm not showing it here, but this is part of the publication that I'm writing right now. But of course, this is a good comment, and I think it is also partially addressed in the synthetic tests, although this is all a synthetic well. But if we take back yes, so if you actually look at this, the difference between this true model here and this true model there, what you can see is that in this type of setting where the basins are very deep and you have a high conductivity in it and the crust is very thin, you actually see a difference in how the upper mantle is recovered. So it might be a bit that the resistivity is quite stretched with the scale, but you can actually see almost an order of magnitude difference at this step. So this is sort of emphasizing my supporting this interpretation, I would say.
Yeah, I would agree with you for the lithospheric mantle part, but I just wonder about the very thin extended crust directly beneath C2. So the very top part of C3. But against that argument is the velocity difference. You have a strong velocity difference, which supports something different there. So wonderful story. Thank you very much.
Thank you.
All right. It seems like we don't have any more questions. I'm happy, with the discussion, and it was very interesting, as Alan said. So, sort of last call, if you want so. Okay, if that's not the case, then thank you very much again, Romain, and we'll see you all, or hopefully all, again next week for Janelle Simpson on using MT to understand the Mount Isa province, so going to Australia. So have a good day, everyone, and thank you very much for attending.
Thank you, bye.